Hi guys, welcome to problem class 1, and we're looking at motion in one direction. So we have a particle here moving on a graph that has velocity versus time, and we're asked to find a couple of things from this. One, which find the acceleration. Two, a couple of displacements. So I'll remind you guys that to find the acceleration, it's just the rate of change of the velocity with respect to time, which is just the derivative of the velocity versus time graph. Well, remember, that's just the slope at a given point. So we can find the acceleration pretty easily here. We're going to have to do it for 4 different sections there. You can see we've got a section here, and then we've got this section here with a positive slope, and we've got this one with a negative slope. But notice the slope is constant, and here the slope is 0 as well. So we have 4 different sections that we can look at. So we'll break it up. We'll say the motion from t equals 0 to t equals 10 seconds. The acceleration, remember, is just delta v over delta t. Sorry, that should be a delta t. Because we're talking about average over that section and the slope is constant, then it doesn't matter. We don't have to use the derivative. So that's, remember, it's the final velocity minus the initial velocity over the final time minus the initial time. So that's going to be 5. So V2 was 5 meters per second if you look at the graph here. And the final was 5 as well. So it's pretty obvious we're going to get 0 for this no matter what the time difference was, but the time difference is 10 minus 0. And that comes out to be 0. So the acceleration is 0 meters per second squared. So there's no acceleration. That makes sense. We haven't had a change in our velocity. It stayed 5 meters per second. There was no change to that. An acceleration is required to have a change, and we have no acceleration. Okay, so in the next section, so from t equals 10 seconds to t equals 15 seconds, you can see we have some positive slope here going upwards, some constant value of slope. So this means our velocity is changing. We must have some constant acceleration that's causing that constant change. And remember, again, we can use our acceleration equals delta v over delta t. That's just going to be, again, from this equation, we're going to have v2 minus v1 over t2 minus t1. In this case, it's 15 is our final velocity minus 5 divided by 15 minus 10 for our time. And we get 2 meters per second squared. So we have a constant value, which is a positive value. That's because we have a positive slope on the graph in that region. So from t equals 15 seconds to t equals 25 seconds, we have a negative slope. See, this is negative. The slope is downwards. So we just have to use our same expression. Acceleration equals v2 minus v1 over t2 minus t1. And we get negative 15. You can see we end at, negative 5, sorry, that should be. Just backtrack. Negative 5. Because we end up at negative 5 here. And we were initially at 15, so minus 15. And the time is from 25 minus 15. That comes out to be negative 20 over 10, negative 2 meters per second squared. So we get a negative answer, so we're consistent with what the graph looks like. Now from t equals 25 seconds to t equals 30 seconds, it's pretty obvious that our acceleration again is going to be 0, but we can use our expression to plug those values in. T2 minus T1, which is -5 minus 5, -5, sorry, divided by 30 minus 25. Got double negative here, so -5 plus 5 is just 0 meters per second squared. And that's what we were expecting for that section. So now we have to draw a graph. The question's asking us to draw, pull up quantitatively a graph of acceleration versus time. So we can draw a graph over here with our axes. This is going to be acceleration. In meters per second squared. And this is going to be time in seconds. And the maximum value we get to is about 2. So we put 2 here, -2. So this is 2 and -2 and 0. And as our time goes on, we go from 5, 10, 15, 20, 25, 30. That's as far as we go. So this is 5, 10, 15, 20, 25, 30. So we've got a little graph there. Now I'll just, I might change over to this color so we can plot that out. So we look at our different regions. For the first region, this one, and that was from 0 to 10 seconds, we were 0. So our acceleration was 0. Easy. For the next 5 seconds, it was +2. So that was that one. Now this one is +2. So our graph jumps up like this for the next 2 seconds, for 5 seconds. The next region, it was -2, and that was between 15 and 25 seconds. So between 15 and 25 seconds, we're now -2. And then for the last little region, we know is 0. So that's what our graph looks like. Okay, that's that first section. So that's the first question answered nicely with all units and our graph. A bit rough in this diagram, but you can make it neater if you like. Now we're asked to find the displacement. So we've just found the derivative or the slope of the velocity versus time graph to get the acceleration. If we want to go back the other way and get the derivative, remember we have to, to find displacement, we have to do the integral. And in this nice easy case, the integral is the area underneath that graph. So we need to be careful of a couple of things, and we'll see how that works. So yes, to find the displacement, the change of position, the question's saying between 10 seconds and 15 seconds. So we're looking for this region here. Basically what we need to do then to find the displacement, it's the integral of the velocity versus time graph. Sorry, my pen's mucking around on me there, just bear with me. So the displacement is the integral of the velocity versus time graph with respect to time. Now don't worry too much about that. All that means is the change in x, so delta x, is equal to the area under the graph. So if we put some limits on the integral there, it's between 10 seconds and 15 seconds. So we're looking for the area under the graph between 10 and 15 seconds. So because we have a nice linear function here, it's reasonably easy. We've got two little boxes, two little sections we can work out. So we can find the area of this guy and then add it onto the area of this guy. So all we need to do is be able to know how to find the area of that box and the triangle. So the area of the box area of the box is just going to be, you can see it's 5, this is 5 here, and this is 5 here. So it's going to be 5 times 5, which is 25. And that's going to be, that's going to have some units. That's going to be meters. Okay, so now we find the area of the triangle. That's going to be half base times height. Half base times height. And that is so it's going to be half. The base is 5. The height, you can see, is 10. So this height here is 10. So we get 25 meters. So the total area under there then, so total area is 50 meters. So that's delta x, our displacement. So we're just finding the area under the curve, or the integral, to go back from velocity to displacement. So the next part of the question is asking us to do something a bit trickier. That's got a little bit of a trick in it that I'll show you. Now what I'll do is just erase. Actually, we don't need to erase it. It should be fine. We can use some different colors. I'll just change to this color. Right, so now we're asked to find the displacement between t equals 20 and t equals 25. So that's this region here. So we're asked to find then this area. We have an issue here in that we're going to get some negative area. Okay, so let's find that displacement between t equals 20 seconds and t equals 25. Delta x is just going to be that integral again, which is going to be the area under the graph. So we're going to go with our half base times height for the first one, plus half base times height for that second area. So that's half. The base is 2.5. You can see this distance here, 2.5. The height again is 5, plus a half. The base again is 2.5, but the height is minus 5. This is very important. Well, you can see from this that this bit here is going to cancel out that bit, and we're going to get 0. So 0 meters. So that's our answer for the second one. There's no displacement. That makes sense because at this point here, we're moving. We're moving at 5 meters per second, and then as we move down, we're going down to 0, and then we're changing around to go to 5 meters per second in the opposite direction at this point. So basically what we've done there is moved in one direction like this, then we've turned around and gone back the other direction for the same amount of time, for the same velocity magnitude, which means that we've got 0 displacement. So this answer now makes sense. Okay, so this question says, a jet airliner touches down at 220 kilometers an hour. It reverses its engines to provide braking and comes to a halt 29 seconds later. So what's the shortest runway on which this aircraft can land, assuming constant deceleration starting from touchdown? So the shortest possible runway has a length equal to the distance traveled by the plane while coming to rest. That would be, basically the plane would stop at the end of the runway, which is pretty much what happens in Lukla Airport. So you should check out Lukla Airport if you want to see something pretty hair-raising as a pilot. So this is a problem of constant acceleration, because the question states that. So we can use one of our equations of motion from the lecture slides. So when we're talking about constant acceleration, we have this set of equations that involve things like the initial velocity, the final velocity, time, acceleration, displacement, all those things. And they work when we have constant acceleration, which we have. So remember, when you approach these kind of problems, you should write down the things you have, the equations that connect them, and then the things that you're looking for. Okay, so you write these things down. So let's write down what we have first. So we have a given initial velocity, we'll call it v naught, and that is 220 kilometers per hour, kph. Now, that doesn't really work for us because we want to use SI units. So we want to change that to 220 divide by 3.6 to get into meters per second. And that is 61.1 meters per second. Okay, so if you're worried about doing this conversion, please check out the videos that I have in the laboratory section. Okay, I have some videos there that explain how to do those conversions. So initial velocity is 61.1 meters per second. That's our SI units. Be very careful about that because we'll try and trick you sometimes by giving you non-SI units like kilometers per hour. The time is 29 seconds. That's how long it takes. And our final velocity, Vf, is 0 meters per second. That's an important parameter to keep note because it mightn't be explicitly given to you, but sometimes it's assumed coming to rest. The plane comes to rest. So I'll just write that at rest. Okay. You mightn't be told that its final velocity is 0 meters per second, but you'll be told that it's coming to rest, or implied that it's come to rest. And so this is the things that we have. That's what we start with. Write them down. What do we want? Well, what we want is, in the question, the displacement. So we're looking for S, displacement. So we've got to think of what connects those. And we go back to our little table of equations from the lecture. And that's our equations of constant acceleration. So we choose the one that has all of those things in it. You know, if we haven't been given the acceleration, we've just been told that it's constant acceleration. Okay, so we can't use any of the equations that have acceleration in them. We have to choose the ones that have all of those in them, those variables in them. And the one that works for us from those slides is the displacement is v naught plus v final divided by 2 times t. Okay, that's just basically saying our average velocity. So displacement is average velocity times time. So that's a simple equation. We can write those values in. So don't put the values in before. So if you need to manipulate this expression, do it with just the variables in it. Don't put the numbers in till the very last bit. So if I had to rearrange this equation for t, I'd rearrange it with the variables first and then put the figures in afterwards. That's pretty important because you get confused otherwise. Plus 0 for our final, divide by 2, times the time, 29. That is 886 meters. That's the shortest possible length of runway. So that's our answer. So the strategy here, guys, write down everything that you have. Write down what you want, and then try and find the equations, all the physics principles that link those two things together. So that's the strategy that if you do this, it'll work for you every time. You won't have to say, which equation do I use? Because it'll become very obvious once you do this. So we're going to extend those concepts to a bit of a trickier problem, a bit of a conceptual problem only. See, what we have in this problem is we have a rocket launching from the ground, accelerating vertically at a constant value of 4.6 meters per second squared. This is great. We can use our constant acceleration equations that we used in the last one. So that makes things simple for us. The acceleration is not changing as a function of time, which makes things much trickier. It passes through a band of clouds 5.3 kilometers thick, extending upwards from an altitude of 1.9 k's. So the clouds start at 1.9 kilometers. I'll just write this on the diagram. So this is another a good strategy is to draw a diagram of what's happening. Okay, so we can write this in. We've got some distance here. So that's where the clouds start, and the clouds start at 1.9 kilometers. And then this thickness here is the cloud band is 5.3 kilometers. Okay, so that means the total displacement there from A to C is going to be 7.2 kilometers. Start writing down things that you actually have here. We have acceleration is 4.6 meters per second squared. We have some initial velocity, 0 meters per second. We have those displacements there. What it's actually asking us to do is find the time. So let's call it TBC. It's asking the time it spends in the cloud. Okay, so these are the things this is all the information that we have. We don't have any final velocities or anything like this. So we have 3 spatial locations, A at the ground, B at 1.9 k's above the ground, and at C, which is 7.2 kilometers above the ground. So we have three spatial locations. But a single equation of constant acceleration can only deal with 2 spatial locations, a final point and an initial point. So we need 2 of our equations. We have to apply the equation twice. So there's a couple of different strategies, and the one that I would choose is this one. If you find another one, have a talk to me about it. I think that there is a few ways of solving this problem. I would apply an equation of constant acceleration to find the time to the cloud bottom. So to find this one here. So let's call that TAB. And then I'd find the time here, call that TAC. And you can see then that TBC, which is what we're looking for, is equal to TAC minus TAB. Okay, you can see that those times TAB and TBC should add up to give TAC. So this is the way I would do it. So we're going to have to use the equation of motion twice, basically, to solve this. So there is another way. You could solve the motion from A to B to get the velocity at B. So find out what the velocity is at this point, and then use that to find, TBC, knowing this distance. So that's another cool way of doing it. So if you can think of another way, let me know. So let's just use my strategy then. So for constant acceleration motion from A to B, choosing, and we always sort of choose, I always write a little symbol like that says this way is up. Okay, so that's our this way is up symbol. So we know displacements in the positive direction are positive, and any accelerations that are positive in that direction as well. Okay, so we have acceleration 4.6 meters per second. We have our initial velocity is 0. We want to find the time to get from A to B. So that means our S. So let's look at our first section. We'll put it in a couple of sections. A. We want to find T. As we don't have this final velocity at the base of the clouds in this form of the solution. So we have S is 1,900 meters. So our displacement is 1,900 meters. The final velocity is missing, so we go through and see what we've got. We've got acceleration, initial velocity, we're looking for time, we've got displacement. So there's an expression that looks like this one. S equals V naught. Oops, sorry about that. That doesn't look like a V naught. So S equals V naught T plus half AT squared. Okay, that's one of our constant motion equations. So of course we're trying to solve for T here, so we're going to have to rearrange this guy around a little bit. So let's do that. So we get T squared on one side. I might do this in a few steps because some of you might not be too familiar with how to do this. So we can say S minus V naught T. So I take this V naught T and I subtract it from both sides and I get this squared on 2. Okay, all I've done is just subtract v naught t from both sides, because I want to just get this t by itself on one side. So I can multiply by 2 on both sides, and I'll get rid of it on the right hand side. So I get 2s minus v naught t equals at squared. If I divide through by a on the right hand side and on the left hand side, I'm going to get t squared equals 2s minus v naught t all over a. And then I just need to square root both sides and I'll get t by itself. So I get t equals square root of 2, sorry, there's something going on with my pen here. Bear with me, equals 2s minus v naught t over a. That's the square root of all of that. Sorry, that's a bit messy. So we can start throwing some values into that now. Now it's pretty good because this bit's going to disappear because v naught is 0, so that's nice, that disappears. And you can notice that I haven't put any numbers in yet until right at the end. So now I can put my numbers in. So I just get, well, let's just write this out a bit neater here. It's 2s over a. Okay, so that's pretty nice. So I get 2s, which is 2 times 1,900, and I divide that by a, which is 4.3. And I get an answer coming out for that one. Sorry, 4.6. So 4.3, 4.6. And I get square root of 826.1. And that comes out to be about 28.7 seconds. So that's the time to go. It's this one here, from the base of the clouds, from the ground to the base of the clouds. Now all I have to do is do exactly the same thing to find this one. So to find this guy here. Okay. So pretty straightforward. So I'll just go over here now, and we just use exactly the same expression, the same working basically. We just use the same expression over here, so we can just use this one here, okay, because our initial velocity was 0, so it's just root 2s on a equals TAC. So TAC, something going funny with my pen, sorry guys, square root of 2s this time is 7,200. And the acceleration is 4.6. And if we do that calculation, we get 55.95 seconds. Great. So now we have these two now. We have these two times. And remember from this argument here, we should be able to work out the time in the clouds, TBC. So TBC was TAC minus TAB, which is 55.95 minus 28.7. And that comes out to be 27.2 around about seconds. All right, so that's the answer. There is another way where you find the velocity at the base of the clouds using one equation of motion and then evolve that with another equation of motion to find the t. You should still get the same answer. So you could check that just to make sure.